Let's jump right into this explainer on offshore well construction and cementing. You know, when you look out at a massive offshore rig churning away in the middle of the ocean, it's incredibly easy to oversimplify what's actually happening beneath the waves. From a distance, to the untrained eye, an oil or gas well just looks like a pipe shoved into the ground. Simple, right? Well, today we're going to look at the reality. We're going to see how an offshore well is far, far more than just a pipe. It's an absolute marvel of modern engineering operating in some of the most unforgiving environments on the planet.
Right off the bat, the crucial thing to understand is that a well is actually a highly sophisticated pressure containment system. Think about what this unseen structure fundamentally has to do. It has to safely and completely isolate multiple volatile geological formations, all sitting at vastly different extreme pressures deep within the Earth's crust. On top of that, it has to support enormous vertical and lateral loads from literally miles of heavy steel hanging beneath the seafloor. Oh, and it has to maintain perfect structural integrity in a highly corrosive saltwater environment while handling toxic gases. It has to endure all of this brutal physical punishment constantly without a single moment of failure for a lifespan of 25 years or more.
So how do engineers actually pull this off? Well, they use a brilliantly engineered Russian nesting doll design. Rather than relying on one single vulnerable tube spanning from the ocean floor down to the reservoir, multiple layers of thick steel pipe, which are called casing strings, are perfectly nested one right inside the other. You start with the widest pipe at the very top, directly at the seabed. Then, as the well pushes deeper into the pressurized earth, the pipes step down in size. This overlapping, layered approach isolates the shifting rock, traps volatile underground pressures, and creates a highly reinforced armor protecting the central production tubing, which is where the actual highly pressurized oil and gas will eventually flow.
Let's build one of these from the seabed down. Step 1 is establishing the structural foundation, and this happens before any actual deep drilling begins. Offshore, this means taking an enormous steel pipe, typically a staggering 30 inches in diameter, and driving it 50 to 100 meters deep straight into the ocean floor. This is called the conductor, and they don't just gently lower it into place either. They will forcefully drive it into the sediment with a massive pile hammer, or they use a process called jetting. Jetting uses high-pressure water to literally fluidize the heavy soil, allowing that giant pipe to sink deep into the seabed. This conductor secures the very top of the well and serves as the absolute anchor point for the immense weight of the casing that comes next. From that massive foundation, the entire construction of the well relies on this strict, repeating procedural rhythm. It goes exactly like this. First, you drill deeper using a specialized bit, while constantly pumping heavy, viscous drilling mud down the hole. And that mud is crucial. Its sheer weight provides the hydrostatic pressure needed to actively hold back the crushing pressure of the earth and prevent a blowout while the hole is open. Second, once you've drilled a section, you pull the drill string out and run a smaller steel casing string down into that mud-filled hole. Third, you pump specially formulated cement around the outside of that smaller casing to permanently lock it into the rock. And fourth, you just repeat the entire process. You drill deeper, use an even smaller casing, cement it, and keep telescoping further and further down. What is truly mind-boggling here is the sheer scale of these dimensions. In a typical deepwater well, the casing steps down systematically. You start with that massive 30-inch conductor at the seabed. Then you step down to a 20-inch surface casing, dropping down to maybe 600 meters. Then a 13 3/8-inch intermediate casing, pushing further down to 2,500 meters, followed by a 9 5/8-inch production casing. Finally, right across the hydrocarbon reservoir itself, you might be utilizing a liner that is just 7 inches in diameter. And that seemingly tiny 7-inch pipe could be sitting at staggering depths of up to 6,000 meters. That is nearly 4 miles straight down into the crust of the earth, perfectly isolated by an ever-narrowing column of steel and concrete. Now, to make this entire telescoping structure hold together, everything completely relies on the cement job. But how do you get liquid cement miles down into the earth and then force it to flow back up the outside of the pipe? Well, the casing essentially acts like a giant syringe. Engineers insert a bottom floating plug into the casing to act as a barrier between the drilling mud and the fresh cement. Then they pump in the liquid cement, immediately followed by a top plug. They push this whole heavy column downward. When that bottom plug hits the base of the casing, a specialized diaphragm inside it violently ruptures. The cement then squeezes through the bottom opening and is forcefully driven all the way back up the outside of the casing, which is called the annulus. It keeps flowing until the top plug hits the bottom plug and physically stops the flow. A valve snapshot, and the concrete is left to cure in the extreme heat of the earth for anywhere from 6 to 24 hours. We really have to pause here and respect the extreme physics at play, because the absolute perfection of this cement job is critical. As the engineering sources starkly note,
An inadequate cement job is a potentially catastrophic failure mode. We've all seen the truly devastating consequences of this with the Deepwater Horizon disaster. If that cement does not perfectly seal the microscopic spaces between the steel casing and the surrounding rock formation, the massive, explosive pressures from deep within the earth will inevitably find a way up to the surface. So, what exactly can compromise this vital seal? Let's break down the specific failure modes. The first major risk is called channeling. Channeling happens when the fluid cement simply doesn't fill that outer annulus uniformly. Instead of forming a solid, impenetrable collar of concrete, you get gaps or channels running vertically up the side of the casing. This is incredibly dangerous because those empty channels act like an open highway, leaving a direct path for highly pressurized fluids to surge toward the surface. You also have risks like an inadequate top of cement, where the pump just doesn't push the concrete high enough up the annulus, or a microannulus forming, which is a microscopic gap between the cured cement and the steel that silently compromises the barrier.
Another profound vulnerability is known as gas migration. Keep in mind that cement doesn't harden instantly. It takes hours to fully cure, and during that time, it transitions through a vulnerable gel-like state. Gas migration occurs when high-pressure gas from the rock forcefully pushes its way into and directly through this partially set cement before the concrete has developed enough strength to resist the flow. It essentially bubbles up through the curing concrete, creating permanent, unsealable voids and completely destroying the structural integrity of the well's primary defense. Because the stakes are genuinely life or death, engineers absolutely cannot just cross their fingers and guess if the cement cured correctly beneath thousands of feet of rock. They deploy specialized acoustic tools to run diagnostic tests called cement bond logs. They send these sophisticated tools miles down the wellbore to literally listen to the pipe. If the cement has successfully bonded to both the steel casing and the rock, the sound waves emitted by the tool get heavily absorbed. This is called high acoustic attenuation, and that deadened sound means the well is perfectly sealed. But if the cement is completely missing or deeply channeled, the bare steel pipe will literally vibrate and ring like a struck bell. That clear, echoing ringing is the terrifying sound of a poor bond, and it tells the team that the well requires immediate intervention. Which leaves us with this final, remarkable thought. When you look at an offshore platform, what actually stands between the ocean floor and thousands of feet of volatile, high-pressure rock? It is nothing more than this brilliant, repeating, procedural rhythm of telescoping steel pipes and perfectly engineered, acoustically tested cement. The sheer audacity of violently driving a 30-inch pipe into the seabed and then systematically telescoping down to just 7 inches over a depth of 6,000 meters, flawlessly managing massive mud weights and immense hydrostatic pressures every single inch of the way, is an absolute testament to human ingenuity. It's truly an architectural masterpiece of extreme subsea engineering. I hope this explainer gave you a whole new appreciation for what's happening deep beneath the waves. Keep learning, stay curious, and we'll see you next time.